Daniel Stilck França is going to give here. It's a pleasure to have you here. Thank you very much for finding the time.
Thank you.
He's doing, from my point of view, one of the best research in this topic now. So it's really great to have him here. And as you know, the course will be from today to Thursday, 2.5 hours per day. And we decided to divide it into 3 blocks of 45 minutes, with 5 minutes of, so you can go to the bathroom and get anything. And that's all. Please, thank you very much for everything, and go ahead.
Thanks a lot, Mika, for the invitation. It's always a pleasure to be here. And yeah, so as Mika said, my name is Daniel. We're going to have a 4-part series course on quantum computing. So if you have any questions, comments, or whatever, just send me an email at dsfranca@protonwave.com, or just approach me while I'm here. Ask as many questions as you like. I also am preparing some lecture notes for the course. So feel encouraged to check them out. So you find them on my webpage. So my webpage is just like my name.eu, and it's under /pages, /notes, bilbao.pdf. Yeah, so let us start. So we're gonna, of course, quantum computing is a very wide topic, very active topic of research right now, and we only have 4 lectures. So we'll only be able to touch the surface, and even then we'll only have to focus on one really tiny aspect of the field. So, and a nice thing about quantum computing is that it's a field at the intersection of math, computer science, and physics. So we also have to pick which perspective we're going to take of the field in this short time, and can cover all of them. And in this week, we're going to take a more, let's say, math perspective of the field. So we will not be talking about how to actually build a quantum computer in a physics lab or anything like that. I'm just going to give you like some sort of the mathematical foundations of the field, so that you can understand the terminology afterwards on your own, and understand how things work and so on. And our main goal will be to understand at least the basics of something called quantum signal processing. In particular, I'm going to try to explain to you how one can solve linear systems of equations exponentially faster with a quantum computer compared to a classical computer. So this will be the goal of these 4 days. This is like already a non-trivial quantum algorithm. And why did I pick this particular path? Well, because first of all, solving linear systems of equations is a problem that appears everywhere. So I think that, you know, if you did any sort of course in STEM, then you certainly had to solve or see algorithms to solve linear systems of equations and so on. So everybody has seen it. Second is that it gives an exponential speed up compared to classical methods. So it's really a problem where quantum computers are significantly more powerful than classical devices. However, the speed up also comes with a lot of fine print. There are a lot of assumptions behind it. The sort of input model and output model is also very subtle. So I think this problem also illustrates the subtleties of quantum computing, because even though it's a field with a great promise, it's important to always look at the fine print and really understand what's going on, so that we are we keep our feet on the ground. Okay, so this will be the objective of the whole week. But today we're just gonna look at the really basics of quantum mechanics and the history of quantum computing, and basics of quantum mechanics from a quantum computation perspective, because I assume that not all members of the audience are already familiar with quantum mechanics. And I apologize if you already know the basics, then I guess it will be very boring. but yeah, I think it has to be done so we can be sure that we're all on the same page. Okay, I should also say that maybe you don't like my style, you don't like my voice, I don't know, you don't like me, who knows. And there, in the notes, I also linked to other lecture notes by other people from the field, so there's some other resources there. Also, the standard reference for quantum computation, which is Nielsen and Schwang by, Quantum Computation and Information by Nielsen and Schwang is also linked there. And two other lecture series in video, one by John Preskill and the other one by Ryan O'Donnell. So these are much more complete and in-depth courses. So I think these are all very great resources if you want to continue studying in this field. So yeah, just already in the first paragraphs of the notes, you find these further references if you want to get deeper into the field. And of course, if there's any particular topic you'd like to learn more about, just ask me afterwards for a reference or send me an email or whatever. I'd be happy to help you out if you want to go further. And of course, you have Mikael here locally who I guess can also help you. Okay, so before we start, I should also continue telling you what this course will not be about. This, as I already mentioned, this will not be a course on the physical implementation, so I will not tell you how to build a quantum computer in the lab. Another very important thing we're not going to talk about is quantum error correction and fault tolerance. So throughout this course, I'm going to assume we're given this perfect quantum computer where we can perform operations without noise and everything works as we want it to work. This is not the case in reality. In reality, quantum computers, first of all, quantum computers exist. You can access them through the cloud. They can already do some non-trivial things, so this is not all science fiction, but the quantum computers we have today, they're noisy. So like whenever you want to do an operation on them, there's a certain probability of it failing. And there are ways of dealing with it, which is the theory of quantum error correction and fault tolerance. But we don't have time to talk about this. It's very important, but we don't have the time. So I'm just going to assume all the quantum computers we have are perfect. And there are many ways of doing quantum computation. For instance, there's adiabatic quantum computing, there's measurement-based, and so on. But we're not going to talk about these alternative models of quantum computation. We're going to focus on something called gate-based quantum computation because it's somehow the closest to how classical computers operate, so it's the easiest to build intuition upon. Okay, so before we start with the introduction to the field, are there any organizational questions you have or general questions? No? Then let's start. Okay, so before we talk about what quantum computers are, maybe a few words on classical computers, let's say the phone in your pocket. So how do they work? Essentially, they are machines that can perform certain operations on bits, right? So you have some bit strings and either 0 or 1, and they perform certain operations on these bit strings. And we see that every year they get faster and faster and faster, but fundamentally the way these machines work is not changing that much. At the end of the day, they can just like operate faster these bit strings of zeros and ones. Okay, so what are classical computers? So you essentially perform gates on bit strings. So just these guys. Now, and if you have faster hardware, let's say you increase the frequency with which you can perform such operations and so on, then you can you get a constant in runtime. But this, I mean that if your computer can do twice as many operations per second as before, then of course you can solve any problem twice as fast in principle, right? But sometimes you also find better algorithms. Okay, so let's say before you had an algorithm that scaled like, I don't know, n squared, and then you find this can lead to asymptotic improvements. In the sense that you can solve problems with, let's say, some polynomial speedup or something like this if you find a cleverer way of solving it. Now, importantly, if a problem requires an exponential number of gates in input size to be solved, no matter which algorithm, we see that no hardware improvement or better algorithms will help. So what do I mean? So if we have some sort of problem that is so difficult to solve on, let's say, your phone, in the sense that no matter which algorithm you perform, the number of operations required to solve it scales exponentially in the size of the input. Let's say the input is again some bit string. Then we can build faster and faster and faster hardware and do a lot of algorithmic research. But if the lower bound is still exponential, then it's just the nature of the exponential is going to be essentially impossible to solve large instance sizes. If we just then double the size of the instance we want to consider, then the amount of time we will need will grow gigantically, right? And then one thing you can ask yourself is, well, what if I build, are these machines then everything we can do? Are like these classical devices we have, like your phone that perform gates on bit strings, the only thing we can do? And indeed, this is not the only sort of proposal in the block, right? So if you study, for instance, classical complexity, people are talking about, for instance, Turing machines, which are another model of computation that is not exactly like this, where you're just performing gates on bit strings. And in computer science, there is this thing called, or this idea called the strong Church-Turing hypothesis. And it essentially says that all realistic, this word is important, models of computation are equivalent. I'll specify what this word means in a second, to a Turing machine. So, like Church and Turing were two pioneers of computer science and complexity theory, and what this hypothesis is saying is that essentially this is all there is. Okay, so like the way your phone operates is more or less the only way of doing computation. Because by equivalent, what they mean is that if I can solve a problem in one model, in one realistic model of computation, then I can solve it in another model of computation with a polynomial overhead. So equivalent here means up to a polynomial. Okay, and if we have a problem that requires then an exponential number of steps, then in any model, it will also require exponentially many steps, because a polynomial of an exponential is again an exponential. Okay? So what this is saying is that if a problem requires exponentially many steps in one computational model, it will require exponentially many steps in all realistic computational models. Now, what does realistic mean? Realistic means that you're not cheating in some ways. So, for instance, you can solve certain problems exponentially faster if you assume, for instance, that your machine has no form of noise in some analog setups and so on. So realistic here means that we are not cheating in some ways, for instance, by assuming that the machines we have will always be perfect, that they will have no noise, or that we can use an infinite amount of energy doing computation and things like that. Okay? So this is what this is saying, that this, up to some polynomial, whatever your phone is doing is all there is to computation. And the main point, or the main dogma of this lecture series, is that this thing is false. We don't believe in this. Okay, so the dogma of this lecture, this is false. If you believe in this, I invite you to leave. You're not welcome here anymore. No, but more seriously, the point is that we believe that quantum computers are a realistic model, and they are not polynomially equivalent to a Turing machine. So just to make the distinction here. So quantum computers we believe they break the Church-Turing hypothesis. So we believe they are realistic. And the reason why we believe they are realistic is that there is, for instance, the theory of quantum error correction and fault tolerance. Okay, so if we want to build a quantum computer, you don't need to for instance, control them through arbitrary precision or have infinite energy or whatever. You just need to build certain components with a certain quality, and then you can do it. So the main reason why we believe they're realistic is due to error correction. And, well, why we think they're not equivalent. So, for instance, there are certain problems we don't believe classical computers can solve efficiently, but quantum computers can. And one example is, for instance, factoring. So we don't believe it is possible to factor large numbers on classical computers. But we have Shor's algorithm, and which says that we can factor integers efficiently on a quantum computer. But there are other examples, and we're going to see here in this lecture the case of solving linear systems of equations. But maybe a few comments. So our whole cryptographic system hinges on this fact that we don't expect to be able to factor large numbers efficiently. But Shor in '95, I think, showed that with a quantum computer you can indeed factor these integers. So this was maybe the first example of a problem where we expect quantum computers to perform exponentially better than classical. But by now we have other examples. Okay. Any questions so far? Good. Now, maybe you don't care about the strong Church-Turing hypothesis, and you don't think that breaking it or showing that this is false and identifying problems that can be solved much faster using this alternative model of computation is an interesting motivation on its own. So maybe I should also mention another reason, let's say more aesthetic, maybe, to study quantum computing, which is that I think it's very nice to be in this topic, or to do research on this topic, because it's somehow at the intersection, as I said, of math, physics, and computer science. So, you know, it gets some of the nicest ideas from these fields in the last few years. So you can do a bit of quantum mechanics, which is lots of fun, but you also need like computer science, but also a bit of information theory. So I think it's a field that mixes some of the most interesting topics of the last 100 years or so. So that's another motivation to be in the field. And before we start with the main definitions, maybe, as I mentioned, Shor, just do a short timeline of how the field evolved. So timeline. So one could say that the field really starts in the 80s. So here we have As was usual back then, you had someone in the USSR and someone in the West essentially having similar ideas, and then only later you discover they were discussing the same thing. So in the let's say USSR, there was the work of Manin, and in the West, I think one of the pioneers was Feynman. And essentially, I mean, this guy was working on logic, and this guy was a physicist, so they came from different perspectives. But Manin was essentially saying, from, let's say, a logic perspective, that given that the fundamental laws of nature are based on quantum mechanics, then we should also have our models of computation based on quantum mechanics, not classical mechanics, which, you know, like Turing's model is very classical, right? So he was coming more from the side of logic, and Feynman was more like coming from the side of let's solve some problems in physics, because he was saying, well, you know, the motivation is very similar. He was saying, well, nature is quantum mechanical. It's very hard to simulate quantum mechanics. So if you want to solve problems in quantum mechanics with a computer, it's very hard. And he was saying, well, maybe we are facing these blocks because our machines are classical and we're trying to solve problems that are quantum. So we should maybe build computers that also respect these laws to then solve problems in physics. So they were coming from different perspectives, but the underlying idea was the same. Nature is quantum mechanical. We should also build our computational devices based on ideas coming from quantum mechanics. So what I said over there, I think I now see is wrong. So in '94, actually, Shor came up with his algorithm. By the way, I'm sorry we won't be able to discuss Shor's algorithm due to time constraints. And I must say, even nowadays, 30 years later, it's still kind of hard to understand what goes on. So this is really a monumental achievement. I think it would take us 2.5 hours to go through all the details of Shor's algorithm, but it didn't come out of nowhere. So a few years before, or some months before, there were some other algorithms that came before that had a similar flavor, namely Touught's algorithm and also Simon's algorithm. And they essentially, Tought we might even discuss today rapidly, but essentially these were people in the early 90s showing that with quantum computers you could actually solve certain problems involving finding the periods of functions and things like that faster. And then Shor saw these ideas and took it to the next level, really, with his algorithm. And I should say just that even though we were already in '94, these like sort of Soviet versus West things were still going on, because there's this interesting anecdote with another giant of quantum computing, who is Kitaev. He's a Russian scientist, and he just heard about the fact that Shor had derived his algorithm through colleagues, but he couldn't get his hands on the paper, so he re-derived it on his own, but through a completely different way. And came up with maybe one of the, let's say, top 4 quantum algorithms, which is phase estimation. So around the same time, we also have like Kitaev with phase estimation, which is an algorithm we're actually gonna discuss. All right, but then, as I said, so Shor came up with this wonderful algorithm saying like, hey, we can solve problems exponentially faster, but then people were like, well, okay, but probably your model of computation then isn't realistic. People are like, okay, with these very interesting machines. You can solve these problems. But this probably just indicates that what you're doing is not realistic. So Shor came to the rescue to show that these people were wrong and came up with the theory of quantum error correction. Showing that it is in principle possible to correct errors when you're doing a quantum computation. So you don't need to build quantum devices which are essentially noiseless and perfect to do quantum computation. It's still possible to have components which fail every now and then, but then you do error correction on top. And then, so Shor in '95 came up with the first error correcting codes, and you'll see at the end of this lecture why this is again highly non-trivial to show that such a thing even exists, that you can correct errors in a quantum device. But importantly, from '96 to '98, we had the so-called threshold theorems. And these are very important. So what are the threshold theorems? They essentially say that if you have, let's say you have a device and you can apply an operation with some failure probability p, okay? And you have these components that all fail with this small probability p. The threshold theorem then says that as long as this failure probability is small enough, but it's like a constant, right? Okay, it's not like something that needs to scale with the size of the computation you want. As long as you can build devices that have a certain quality, you can use these components to simulate essentially noiseless components, okay? So it's like saying that you don't have to build a perfect chip to simulate a very large noiseless computation. All that it matters is that you get them to be good enough. So after you reach this constant level of quality, it's fine. And this exact number depends on the sort of code you have and the assumptions you make and so on. But this is one of the reasons why we think quantum computing is realistic, because we have this threshold theorem. Okay. And maybe another important development in '96 is Grover's algorithm. So what is Grover's algorithm? It's a quadratic speedup for unstructured search. So, you know, the easiest way to write a paper in quantum computing is to find an application of Grover's algorithm. I think we've all done it. What does it do? So Shor's algorithm is for factoring integers, as I mentioned before. I mean, factoring integers is a very specialized problem, right? It's not something we do every day or that pops up on every sort of situation. It's really restricted to more, let's say, cryptographic applications and so on. But Grover's algorithm, on the other hand, gives you a quadratic speedup. What is unstructured search? Let's say you have a list, okay, let's say you have a deck of cards and you're searching for a card, and the question is, how many cards do you have to look at before you find the card you care about? And if you have a deck of cards with n cards, if you do it classically, you have to look at like order n cards. In the worst case, it will be the last card you look at, right? But Grover showed that if you have some sort of quantum access to this deck of cards, we're going to see it today, what this means, then you can do it with square root of n queries or looks at the deck. And unstructured search is something that appears everywhere. Like you have to find some sort of marked element on a list. This is a problem, I don't know, like this morning I was not finding the key card to my hotel, right? So with Grover's algorithm, you have to look at less things before you find what you want. And this is, so even though here the speed up is quadratic and not exponential like this one, it's much more universally applicable. Okay, good. And maybe just to finish this timeline, because this is in 96, again, almost 30 years ago. Let me just mention where we are right now. So I would say that now, let's say 21 until even very recently, 24, what are we seeing? We are seeing the first demonstrations of quantum error correction. So there are now several there were several fundamental papers in the last few years. So just to mention, I think the last big breakthrough was by Misha Lukin's group at Harvard, beginning of this year. But there were other important breakthroughs like the one by Andreas Wallraff's group at ETH in 21. So even though we know in principle how to do error correction since a long time, performing those operations in practice is extremely difficult. And because it requires a very fine experimental control. And a lot of people, for instance, Gilles Calais, he's one very famous critic of quantum computing. I linked to his blog on the notes where he rants about quantum computing. Say, for instance, that, okay, this is all nice and well, but you'll never be able to do it in practice. And until rather recently, one could say, yeah, indeed, many of the important operations required for error correction were never demonstrated experimentally. And I'm not saying that we now know that doing error correction is trivial and everyone can do it. It's still like very few people, and they can only do it in a very restricted way. But the point is that we're making a lot of experimental progress in this direction. So it doesn't look like something crazy anymore to do error correction at a large scale. Maybe it's something that is even feasible in the next decade or so. But I would also add that in the last 5 years or so, we maybe have reached quantum advantage. So maybe you've heard about certain experiments. For instance, the first big one was performed by the Google group, where they claimed that even before they were able to do quantum error correction, even using these devices we have these days, which are very big but very noisy, they could perform computations using a quantum computer that no classical device could do. So even if you took like the world's largest supercomputer, you could not do this, okay? And the first one, I mean, these claims have been coming and going for the last years. And the reason why I put the question marks over here is because if you're following this, you know that this is like a very dramatic telenovela with lots of ups and downs, okay? Because what happens is that someone puts out a paper, and then sometimes it takes weeks, sometimes it takes years, but people then say like, no, we came up with this very clever way of simulating whatever you're doing. And so I would say that there's a lot of debate whether we already performed one computation that is impossible to do with a classical device, but that we can do with the quantum computers we have right now, okay? And how much, let's say, credence you should give to these claims depends a lot. It varies a lot. So for instance, for the 2018 Google experiment, they wrote in the conclusion that it would take 10,000 years to do this on a classical device or something like this. And it took maybe like, let's say 1 to 2 years for the community to be able to simulate whatever they were doing. And then maybe 2 years ago, we also have a proof that even like from a complexity theory perspective, whatever they were doing is not difficult in the sense that they're polynomial time classical algorithms because of the noise. So noise is very important. But there are some other ones that are, let's say, that take less time to break. For instance, one that was particularly dramatic was one by IBM last year. It was like the cover of Nature, and they claimed they could do a useful computation with their machine. And then literally 1 or 2 weeks later, there were, I think, 3 or 4 different groups in the world who showed they could do it easily on a laptop, okay? So all these claims, take them with a grain of salt, but I think that the fact that we're discussing this is super exciting already, okay? Because like when I entered the field, which isn't even that long ago, it was very clear, like nobody would dispute that whatever you were doing with the quantum devices we had was useless, and you could simulate it maybe even like by hand, okay? And now we are at the point, let's say 6 years later or 7 years later, where it's unclear. We could debate and so on, and this transition from obviously useless to maybe, who knows, let's look at this in detail, is already quite significant, I think, and makes me, especially combined with these advances, I think it's a really exciting time also from like a technological perspective to be in the field. So there are thousands of different platforms also. That's another thing I should say. It's not very clear right now like how you should build a quantum device, what's the best way, because there are like optical devices, superconducting qubits, neutral atoms, and so on. Different platforms have different number of qubits with different quality, with different caveats, and so on. So also the state of the art from, let's say, a physical implementation side is very complicated, and it's difficult to have an overlook. I put 2 nice figures in the lecture notes. One of them shows all the different physical implementations and the companies or main research groups that are following them. And another one with how many qubits different people have. These are wildly out of date because I think they're 2 years old. And as I said, things are progressing rapidly. But at least it gives you some idea of where we are. Okay, so this was the blah, blah, blah section of the lecture, just to give you some context and introduction. So are there any questions, comments before we move on? To continue, Mikkel already mentioned that there are some important things I did not mention here. And of course, like, I mean, here you see that there's a big gap, so that this already indicates there are important things I missed. But maybe some things that happened in the 90s were that people, especially there's this paper by Stilck and Sola, I forgot the exact year now, that I should have included for sure, because it was sort of the first proposal of a physical platform where you could construct quantum computers. So they're like, hey, there's this physical system that, it's not crazy to think that you can control it this in this way, and then you can build quantum computers. This is the idea of ion traps, if I recall correctly, and that's something people are still pursuing these days. So in the 90s, there were also some important papers saying like, hey, these are physical systems where you can actually build, that you can actually use to build these devices. And also like some work by Vazirani, also one of the, let's say, fathers of quantum computing. There are two Vaziranis, they are brothers. There's Umesh, who works in quantum computing, and the other one, I forgot the first name, but Umesh Vazirani, who sort of connected also the physics and the computer science and so on. So this is, of course, a very condensed thing, and I forgot also many important things, so don't think this is a complete thing. All right. Let's now continue by just doing a 45-minute crash course on quantum computing, on quantum mechanics, sorry. Because we're finally gonna set our notation. And I think if you're coming from math, then probably the easiest way of understanding quantum mechanics is to make the comparison with classical probability theory. So you should think of quantum mechanics as a way of generalizing probability theory. And what do we have, let's say, in probability theory? And I'm only going to do discrete things, so we don't have to think about like measurable spaces and things like that. So let's see how we build a probabilistic theory. So there are a couple of things we need. We need a state space. So this is going to be some set of states which are going to be from 0 to d minus 1. As I said, this is all going to be discrete. So for instance, if d equals 2, then we are indeed just thinking of, let's say, a coin, heads or tails. And when we don't have perfect knowledge of what's going on in the state or the outcomes, then we can just assign a probability to each outcome. So for instance, if we have d equals 2, we can represent the probability of outcomes with a vector p in R2. So, no, p is a bad choice. Let's call it big P. And this is just, something like this, where this is the probability of, say, 0/heads and 1/tails. And you just have that P is an element of 0, 1. Okay? So, nothing too interesting going on so far. But all I wanted, the thing you should consider here is just that I have specified a state space, and then I've told you how we can represent different probabilities for different events in this state space, which is just like a vector of unit norm. Okay. So, in essence, all we need is 3 things. So to get a theory, we need to identify possible states. then we need a way of assigning, so let's call this thing number 1, number 2. Then we need a way of assigning probabilities. And number 3, we need to specify a way how we can transform the state. And these two are sort of pretty easy, right? So for instance here, if you want, let's say, the probability of observing 0, you just look at this entry of the vector. Or if we have more states, we could, like, I don't know, let's say we have 4 states. You look, what is the probability that I have 0 or 1? You just sum up the first 2 entries and so on. So we know how to do these things for classical probability distributions. And the transformations are also not too complicated. So in fact, for instance, if you want to, let's say, if I tell you to flip the coin, right, then all you can do is to apply the following transformation. Let's do some examples. If you want to flip a coin, then all you need to do is to apply the matrix X, which acts as follows, right? Because if you multiply the P with this matrix, you see you're just gonna flip these 2 entries, right? So if before the probability of heads was P, now after you flip it, it will be 1 minus P. So generally speaking, reversible transformations are permutations. So if you have some sort of state space and you want to transform it in a way that it's reversible, that is, if I do something to it, I can go back, then it's not too difficult to convince yourself that the right way to model this is by looking at the sets of all permutations of your state space. Okay, and you might ask, oh, why are you talking about reversible transformations or bijective transformations? Well, because in quantum mechanics, we're only in principle able to do such things. So I'll restrict to reversible for classical here. So, and there's another aspect that maybe isn't so important at first when you consider classical systems, which is that you would also like to have a recipe to combine random variables. /systems. That is, if I have let's say not 1 coin, but 5 coins, you would like to have a standard way of describing what happens to these 5 coins, right? And classical probability theory, let's say you could take then the state space to just be the Cartesian product of the individual state spaces, and then you just have a larger probability vector to describe the possible outcomes. But in principle, these are the 4 rules or the 4 elements of the theory that we'll need to generalize. Okay? Now, how do we do this in quantum mechanics? So In so in quantum mechanics, the first thing we're going to define is the state of a system. So we will say that the state of a system with state space of size d is given by some unit vector psi element of CD. Okay, and this is just the Euclidean norm. So, by the way, there's something I have problems with, which is being consistent with whether I start counting from 0 or 1. So I'll make this mistake at some point. I apologize in advance. So what is the state space? Like before, we were just looking at, so for probability distributions, it's just some vector p with all the entries positive, and they have to sum up to 1. For quantum, the corresponding variation of a probability vector is now a complex vector in CD, and it has to have L2 norm equal to 1. Okay? All right? So once I tell you how to represent a state, I also have to tell you how to assign probabilities to different outcomes. And this is done through what is called a measurement. And a measurement is given by a set, let's call them Pj actually. Pj equals 1 m of matrices with Pj an orthogonal projection. So recall that a matrix is an orthogonal projection if it squares to itself and is self-adjoint. And you have that they are like a partition of unity. See, I already told you here, I started from 0, now I started from 1. Sorry about that. It's going to happen. Okay, so, yeah, and, please let me know if any of the terminology is not clear. So, I tell you now, I told you what is a state. I told you now what is a measurement. Okay, and now I'm going to tell you how to assign probabilities to different outcomes. Okay? So, forgot to give it the name. So there's Born's rule. So given a measurement Pj, j equals 1 until m, and pure state psi. Oh, I already started using brackets, sorry. The probability of observing outcome j is P of j psi okay, so we just project the vector psi onto direction j and look at its squared norm. Okay, so I'm just telling you this. I understand that this might be a bit strange now, like why are you defining things this way? But for now, just accept it. And maybe one historical comment, even though it's called Born's rule, and Max Born was indeed the first person to write this thing down. But the funny thing is that he got it wrong the first time. So in his original paper, he first wrote this without the square. And then there's a footnote saying like, oh, careful reconsideration shows that actually the right way to go is this. So, you can get your name attached to something very important even if you get it wrong the first time, which I guess is nice. Okay, so let's prove our first very trivial result, which is the following. I'll first explain, we'll first now see that this makes sense. So, lemma P is a valid probability distribution. Very simple proof, but important. So the two things we need to show are that P of j is positive and sum j P of j equals 1. So to show 1 is not too difficult because I've already done it for you essentially, right? Because even though we defined it this way, so maybe we can use this. We'll see why it makes sense to use orthogonal projections, right? Because how do you go from this equality to this one? Well, we have that psi pj psi is equal to psi pj psi, and this because it's a projection, right? And I can put this thing over here and it will be pj psi pj psi, which is just pj psi squared positive. Is this clear to everyone? Oh, I forgot to mention an important thing. So even though I'm also a mathematician by training, I was already corrupted in some senses. In particular, I think the scalar product convention of mathematicians is terrible. So throughout the lectures, I'm going to assume it's like linear on this argument and anti-linear on this one, which mathematicians do it the other way usually. But I don't think it's a good convention. Anyways, so this is how we see that indeed it's positive, and we see why this requirement here makes sense. Any ideas what we need to use to prove the second? Sorry, I already pointed at the thing. This one, how to prove it? Just well, what you do is we just write down the definition, right? This is just psi, pj, psi. And, well, we can pull this sum in. So this is psi, sum j, pj, psi. It's a measurement, so I assume that this sums up to the identity. So this is psi identity psi, which is just the norm of psi squared, which we assume is 1. So all good and easy. Okay, questions? No? Then maybe two remarks that are important. First of all, note that I only defined probabilities in terms of norm squared. Now, if I had, instead of the state psi, I actually had some e to the I theta psi. So I multiply it with some complex number of magnitude 1. What would happen here? Well, this would not change anything, right? Because if we look at what happens here, it would be pj ei theta psi square. This is just a scalar. We can pull it out of this norm. So this is just pj psi squared. So we see that the probability will not be influenced if we multiply our psi by some complex scalar of absolute value 1. So actually, it turns out that pure quantum states are only defined up to a complex phase. So ei psi phi is equivalent to psi 4. So in fact, I was sort of lying. This is not the let's say the cleanest way to define things, because actually states that are the same up to some global phase are in principle exactly the same. So you could say that like the correct state space is like projective space and whatnot, but yeah, I think this is just simpler to work with, and always keep in mind that if you multiply by a complex number, it's perfectly you don't change anything, and the reason why you don't change anything is because the probabilities of outcomes is going to be left invariant by such a multiplication. Okay. All right. Another important, so just for you to get used to, let's say if you consult textbooks, especially in physics, they will call psi the wave function. So if you read somewhere the term wave function, they just mean this. But usually they are not, if you go to physics textbooks, they're not defined in discrete spaces. They're usually like some psi, some L2 of, I don't know, Rn or something. Just some other Hilbert space of your choice. But we'll be doing finite dimensional stuff. So in quantum computing, most of the time, you only care about finite dimensional spaces. But in physics, people usually work with, let's say, separable Hilbert spaces or something like that. And yeah, what else did I want to say about this? Maybe some of you are asking yourselves, why did I define things this way? And I think that's a very valid question. We don't have time to discuss it, but if you maybe want to see one way these structures emerge more naturally, I would encourage you to download, Google Gleason's theorem, which tells you essentially, which gives you some assumptions on state spaces and things like that that make this sort of Hilbert space structure emerge naturally. All right. Now let's do some examples. Maybe erase this bit. So in quantum computing, you will often hear about qubits. Now, what is a qubit, or what is the state of a qubit? Oh no, I forgot one important comment, sorry. You might be asking yourself why I wrote pure quantum state here, right? Not just quantum state. It turns out that I'm sort of cheating because this is not the most general way of describing the state of a quantum system. For instance, with this formalism I've written down, you cannot model things like, with a certain probability P, I'm gonna create one quantum state of some probability 1 minus P, another one. This is also not a very good framework if you want to represent what happens with quantum systems under noise. But this is, so this is restricted. If you wanted to do things in full generality, you would have to work with something called a density matrix. But we will not require this formalism later, and with quantum algorithms, usually it suffices to work with pure states. Yeah, just for you to know that there's more to quantum mechanics than this. Actually, this is also not the most general formalism for measurements and so on, but this is, let's say, the minimal formalism we need to describe 99% of quantum algorithms, so that's why we don't do it more generally. Okay. All right. Let's do the first example, which is the qubit. So maybe you all heard the word qubit before, and this is like the basic unit of quantum information, what the bit is for classical systems. And a qubit, the state of a qubit, can just be described by some vector in situ, really. So the state space of dimension 2. So you have two possible outcomes. And how do you describe it? Well, it's just some vector alpha beta with alpha squared plus beta squared equals 1. And as I said, this is only defined up to what is called the global phase, right? So if I have instead ei theta here, ei theta here as well, it's the same state. But yeah, in principle, all you need to describe a qubit are two complex numbers that square to the identity. Okay, now another important example. So this is an example of a state. Let's now do an example of a measurement, and this is the computational basis measurement. So this is also something you hear a lot if you look at quantum computing textbooks or whatever. People will be talking about computational basis measurements all the time. What does it mean? So you let ei I equals 0, d minus 1 elements of CD be the canonical basis. And then we define Pj to just be, maybe I should define them with j's as well, to just be Ej star Ej. So this is really just the projection onto the direction of Ej. Did I messed up the stars, right? Sorry. Then Pej are the operators of the computational basis measurement. And if you are more comfortable with matrices, you just have that Pj is just like 0, 0, and then here if you have the jth row, here you have the jth column, then here you have a 1. So you have a 1 in the jth diagonal and entry and 0 elsewhere. And then it's not too difficult to convince yourself that if you sum up all the Pj's, that this will indeed give you the identity, right? Because each one of them is giving you one of the identities. It's also not too difficult to convince yourself that this indeed holds, right? If you square this thing, you also just get a 1 here again. And let's do a third example, which is going to be measuring a qubit. So what I'm going to take now is the computational basis measurement for a qubit. And I'm going to label this result over here as 0 and this result here as 1, right? Because I take P0 to be the projection onto this space and P1 as this space. So if we measure psi equals alpha beta in the computational basis, what is the probability of measuring 0? Does anyone see it? Well, let's do the computation. It's like psi, then we apply p0 psi, right, and take the scalar product. So what we need to do is to compute this thing, right? What is p0? p0 is just 1, 0, 0, according to that thing, right? So if we apply p0 to psi, which is alpha beta, all we get is alpha 0. Now, so we now need to take this scalar product. So we need to take the scalar product between the vector alpha beta and the vector alpha 0. Remember that when taking scalar products with complex numbers, you have to take the complex conjugate, right? So this is complex conjugate of alpha times alpha, which is absolute value of alpha squared. Okay? And what is now the probability of observing 1? Any question? Any guesses? I know it's not too complicated, so just anyone? Thanks, yeah. I appreciate that. Okay, so in particular, we see that, I mean, we already proved it, but we see that indeed, if we take the probability of observing 0 and the probability of observing 1, we get 1, right? Because this is normalized. So, for instance, there are famous examples of states. So, so there is something people like to call the plus state, and it's this vector. And you see that if we measure it in the computational basis, it's going to be 1/2 probability of observing 0, 1/2 probability of observing 1. Now, look at how strange. There's also the minus, where you have, well, a minus over here. And if we measure it in the computational basis, then you observe the same thing, right? Like this one with probability 1/2 and this one with probability 1/2 again. But the funny thing is that they are not the same, right? Because, you know, I said, for instance, that they are the same if they only differ by a global phase. And you cannot just change a global phase here and map them onto each other. So they're not the same. But I mean, this guy is equivalent to minus 1 over square root of 2 and 1 over square root of 2, right? I can multiply by a minus here and they're still the same. But when we measure them in the computational basis, they turn out to be the same. Now, there is another important qubit state, which is the 0, which is just this thing. And there's the 1. By the way, I'm going to explain these weird things in a second, okay? It's just take it as for granted now. And when we measure this one, well, we observe 0 with probability 1. That's why it's called 0. And this one with probability 1, we observe 1. Okay? But funny thing is that, as I said, these two, when we measure them this way, they gave exactly the same statistics for the results. So they're somehow indistinguishable. when we measure in this basis. Whereas these two have very distinctive behavior, right? With this one, we always observe 0, always observe 0, always observe 1, so it's easy to distinguish them in this basis. Now, just a last comment. You could also define the measurements Q0 equals 1/2 1 1 1 1 and Q1 1/2 1 minus 1 1 oops 1. I won't show that they square to the identity. If you're very bored, you can do this computation. But sorry, that they square to themselves, that these are indeed projectors. But it's easy to see that they sum to the identity because the off-diagonal elements only cancel out. And it turns out that if you do this measurement, if you do the computations, and I encourage you to do this computation, I think it's nice to see how things work. It turns out that if the state is this one, is this one, you're going to observe Q0 with probability 1. And if this one, you're going to observe Q1 with probability 1. But if the states are these ones, the probabilities will be 50-50 again, if you're doing this measurement. So we see that some states sort of look the same when we do a measurement, depending on how they look in a given basis, okay? So even though these states are specified by these complex numbers, whenever we perform a measurement, we're only able to access them this way. So if you want to, like, for instance, extract information about this alpha and beta, we need to measure in a bunch of different directions and combine this information. And it might even be the case that different states actually yield the same result when you're measuring them in a certain way. But we're going to see a lot of examples of this later. This is just to give you a taste of these sort of phenomena. Okay, so yeah, these are the basic computations of how you specify a state and how you compute measurement outcome probabilities, okay? And for instance, a computational basis measurement is exactly the sort of thing you can do on a, let's say, standard quantum computer. So if you look at the quantum computers you can access through the cloud, what they do is, like, they will prepare certain quantum state, and then you can measure it in the computational basis. That's why people call it computational basis, I guess. All right, so there are two things I didn't tell you yet, which is how to transform quantum states, how to manipulate them, and how to combine quantum states. So if I have, let's say, not only 1 qubit, but 60 qubits, how do I describe this state space mathematically? But before we do that, any questions? And yeah, maybe just one comment. I think it wasn't very clear before, but the notes, they are already available, but they are not explicitly linked on my website. The reason is that they're still, like, I'm going to construct them throughout the week, so I didn't want people to, let's say, access them while they're not very clean yet, except for you. So let me just put the link again in case you went to my website and looked for an explicit link. I guess maybe tomorrow I'll link them explicitly and put a password or something. But here is the URL. It will take you directly to the PDF, okay? Notes Bilbao.pdf. All right. Now, let's do transformations. So in quantum mechanics, transformations are described by a unitary matrix U, just D by D matrix. Okay, so recall that you have a unitary if U star or U dagger, depending whether you prefer physics or math conventions, equals identity. So if you multiply it with its adjoint, you get its inverse. And why? Well, they are the natural class of linear transformations that preserve the state space. And why is that? Well, you have that for op psi, we have that u psi, the norm of u times psi is the norm of psi. That is, they respect the norm. So if I have a state, recall that all I need to have a state is a complex vector of unit norm. So if I start with something that has unit norm, so if this thing here has unit norm, then, well, u times psi will also have unit norm. So unitary matrices are the are the natural sort of set of linear transformations you consider. And in some sense, a quantum computer is a machine that tries to implement very big and complicated unitary transformations. We'll see in a second how. But before that, there's the last ingredient we need, which is how to combine systems. Okay? So just one question before we continue, so that I see how much detail I give to this bit. How many of you are familiar with tensor products? Or, okay, so I see not everyone is 100% familiar with them, so I'm just going to explain some basic properties in a second. But let's do composite systems. So we know that if we have one particle or one thing, right, then the state space is described by one CD. So if we have n particles with state space CD, their joint state space is CD to the tensor n. Okay, and here this is the tensor product. So what? Let's maybe just define it quickly formally. Okay, so if so, just like in intermezzo, tensor products. I'll just define it for two, and then you can define it for more inductively, okay? But let's say, so if we have two complex vector spaces, if CD1 has basis EI and CD2 has basis Fj, then CD1 tensor CG2 is a space with bases E1, EI, Fj with I ij. So we take all possible combinations. Here I'm doing everything formally, okay? So I'm just saying, like, here I have one basis, here I have another basis. So this is in particular a vector space of dimension d1 times d2, right? And for quantum mechanics, scalar products are important. So I define the scalar product between EI tensor F, EI1, J1, EI2 tensor F, J2 to be equal EI1, EI2 times Fi J1 okay. So I just take, if I have these tensor products, their scalar product is defined as just like you take the scalar product between these bits and these bits. Okay, and then you extend linearly to the rest of the space. What do I mean? Well, I just told you that these guys are a basis for this vector space, right? I told you how, so I can expand any vector in terms of them. And and then I told you how to compute the scalar product in the spaces. So you just expand any vector linearly, and then you evaluate these things. Okay? So this is how we can formally define the tensor product. And now we'll see in a second why this is the natural way to look at composite systems for quantum. But just before that, let's also look at how the tensor product works for matrices, because this is going to be important. So if we have two matrices A and B, okay, and I'm just going to say that A is going to be like A11, A12, A1n, not n, sorry, D1 and D1, D1. We let A tensor B to be equal. First, this is a D1, D2 by D1, D2 matrix. How do we build it? Well, essentially on the upper left corner, we multiply it by, we'll just have a bunch of copies of B's, and they will all be weighted with respect to the entries of A's. Okay, so what you do in the first row, first column, you put a copy of B, but you weight it with the entry in the first row and first column of A. And then You do the same here, and then if you look at column row K, column L, you just put AKLB there, and that's how you get away with it. But for instance, here at the bottom, you put this one. And the important property when we define tensor products this way is that we have that this is something you can check, that if you have, oh, sorry, and I forgot to tell you how you do it with vectors. So if you have a psi1 tensor psi2, it's the same concept. So if you have your alpha and beta over here, let's say you have just a qubit, then this is just alpha times psi, beta times psi. So again, like you only have one column here, so you can think of this as just a variation of that one, right? So what you do is first row, first column, you put a copy of psi 2 with this weight, right? And then second row, first column, you now put a weight beta, right? And the important property is that if you do A tensor B times psi1 tensor psi2, what you get is A psi1 tensor B psi2. So these things talk well with each other. All right. Questions on this 2-minute or a bit more explanation of the tensor product? Then so I told you that their joint space is CD tensor n. So for instance, if I have n qubits, then the space is just C2, tensor C2, tensor C2, tensor C2, and so on n times. So for instance, C2, 2 qubits is Sin2. It's C2, tensor C2. As we saw here, this will be a vector space of dimension 2 times 2, which gives 4. So this is the same as C4. But if we have n qubits, then we have C to the 2 to the n. So dimension 2 to the n. So we see that the number of parameters we need to describe the state of n qubits grows exponentially with the number of qubits, which is one of the reasons why quantum computing is powerful. I mean, it's also true that if you look at the state space of n bit strings, it also grows like 2 to the n, right? So this isn't the reason alone, but we'll see why it's sort of different from classical now. Okay, and why would you do it this way? Okay, the reason for that is modeling independence. So if you have, in classical probability theory, if you have 2 independent coins and you want to ask, let's say, x1 and x2, and you ask what is the probability of x1 being head and probability of x2 being head, if you know they're independent, how do you compute this thing? Well, you take the product, right? So independence really is the sort of product property for probabilities. And we want to mirror the same thing with quantum systems. So note here that I have some sort of product property over here, right? And this is exactly what we want to mirror it. So if we perform a measurement Pi on one system and Qj on another, we can define the joint measurement as P1 tensor Qj. And now I label the outcomes not only by I and j, but also the pair. So like this would be what happens if I measure the first system, the outcome of the first system, and then measurement outcome of the second one. And if I have if two quantum systems are with states psi1, I haven't introduced this, psi2 are independent, then their joint system is psi1 tensor psi2. And why is this a reasonable definition? What is the probability of observing outcomes I and j? Well, let's use our definitions, okay? The joint state of the system is this, okay? So on the left, I have to, this is our state, and then I told you that the probability of the operator corresponding to ij are these things. So I have to put this thing, and then everyone agrees that this is the computation I need to make. Good. Now, because of this fact over here, I know I can pull it in, right? So this is going to be psi1 tensor psi2. And then I'll have pi psi1 tensor qj psi2. And what is the other property we're going to need? Oh, this one. Because this tells us that this thing is nothing but psi1 pi psi1 times psi2 qj psi2. And this is nothing but the probability of observing pi in system 1 times the probability of observing j on system 2. So this is pi times pj. So we see we recover exactly the same formula of independence as before. So that's why we use the tensor product, because when we define things in this way, we naturally recover the concept of independence, giving us this product rule. Okay? But at the same time, it makes things complicated, because if you have to consider the system of n particles, then this gives us 2 to the n parameters. Now, any questions so far? No? Okay. Then maybe before we do quantum circuits, I would just like to quickly introduce you to something called the Dirac notation. I was discussing with myself whether I should do it or not, because it's a short course and maybe you can live without it, but I decided no, it's actually important. So in quantum computing, or in quantum mechanics in general, right, as you probably already started seeing, we do a lot of scalar products, and we'll do a lot of tensor products. And the standard notation for vector spaces is then not so nice to work with. And because of that, people like to use the Dirac notation. So what is the Dirac notation? It's also sometimes called bracket notation. And essentially what you do is, if you have a vector, let's call it x in CD, instead of writing it as x, you put these sort of brackets around it, okay? And if you have a vector y, which is an element of the dual space, then instead of writing it like this, you write it like this. Okay, so this thing here is called a ket, and this thing here is called a bra. And then instead of writing the scalar product like this, you just write it like this. So they combine nicely, right? And if you want to do a matrix instead, so let's say you want to do like let's say a matrix with column, row I and column j. This is 1 and the rest is 0. You can also express it in this language as EI, EJ, because this matrix is nothing but this thing, right? So when you could represent something in this form, you could instead, in quantum computing, we instead just do like these bras and cats. Okay, so it's maybe takes some time to get used to, but there's nothing too important going on. But when you're multiplying matrices and things like that, I think that this notation is nicer than this one. And when you do composite systems, it also shines. Because I told you before, for instance, that we call the 0 this thing. And then you could consider, for instance, the tensor product of 0, and it turns out to be this vector. But instead, when using bra-cat notation, we just put it like this. We forget the tensor products. And for instance, instead of doing psi1 tensor psi2, we just write it as psi1 psi2. And it's just more economical. Okay? All right. So now that we established this Dirac notation, let me just illustrate one state that is very interesting, maybe one of the most important states. Which is the maximally entangled state. So this is the state psi on C2 tensor C2. So this is a 2-qubit state. And psi is given by 1 over square root of 2, 0, 0, plus 1, 1. So let's get used to the notation. Recall that 0 is just this vector. I had just written it down over there as well. 1 is this vector, so just canonical basis vectors. So this, if you do the tensor product, is 1, 0, 0, 0. And this is 0, 0, 0, 1. So if we write this out in the standard notation as a column vector, this will be 1, 0, 0, 1. Okay. Now, why is it called maximally entangled? And I'm not going to give you a very good answer because, again, like maybe you've heard the word entanglement before, and it plays a very important role in the foundations of physics and quantum information and so on. But it turns out that you can do a lot of quantum computing without understanding entanglement well. So we're not going to discuss it in any depth. But let's see what happens if we measure psi in computational basis. Well, what are the operators? The measurements were like P0. It was this thing, right? This diagonal matrix. But I want you to convince yourselves that this is the same as 0, 0, 0, 0. let's convince ourselves of that. Well, what is this vector over here? This is the vector 1, 0, 0, 0. And this is the vector, right, 1, 0, 0, 0. And if you do this multiplication of these two matrices, you see that it's indeed this one. Okay. So I could also instead label this thing as 0, 0. Okay? And then we can also do P 0, 1, which we can interpret as 0, 1, 0, 1. And in matrix form, these are just 0, 1, 0, 0. I'm just writing down the diagonals, 0, 0, 1, 0. And this is 0, 0, 0, 1. Okay. Now, let's compute the probability of measuring different outcomes. So what is the probability of measuring 0, 0? That thing is going to be what? It's going to be psi p 0, 0 psi. And I'll do this super fast now, just to show you that the Dirac notation is indeed very good. So let's first compute P 0, 0 psi. And this is going to be 0, 0, 0, 0 applied to 1 over square root of 0, 0 plus 1, 1. How do I do this? Well, this bit here is telling me I should take the scalar product with 0, 0 and then weigh this with 0, 0. So if I take the scalar product with this one, I'm going to get 1. And if I take the scalar product with this one, I'm going to get 0. So this is 1 over square root of 0, 0. So it follows that P 0, 0 psi, the norm squared, is 1/2. So we see that the probability that I observe the outcome 0, 0 is 1/2. See in a second why I want to keep this equation. What is the probability of 1, 1 on psi? Similar, projection 1, 1. What happens? It's going to be 1, 1, 1, 1 applied to 1 over square root 0, 0 plus. And again, if we take the scalar product of this one and this one, it's going to get 0. Scalar product of this one with this one is going to give 1. So this is 1 over square root of 2, 1, 1. The norm of this thing 1/2. So we see that the So we see that the probability of observing 0, 0 is 1/2. The probability of observing 1, 1 is 1/2. So in particular, the probability of observing 1, 0 and 0, 1 has to be 0, right? Now, why is this interesting? We see that when we measure this state, the two outcomes will always be perfectly correlated, right? If we measure 0 on the first one and 0 on the second one, then, if we measure 0 in the first one, we know the second one will also see 0. And if we measure the first one in 1, we know the second one will also be 1 with probability 1. So in particular, we see that these systems are not independent. They cannot be of this form. Why is that? Because if they were independent of this form, then we would need a product structure. So let's say if there is a non-zero probability of observing 0 on the first one and 1 in the second one, then the joint probability of 0, 1 also would have to be different than 0. So we see they're not independent. And why this is super strange is that in principle, let's say I have a 2-qubit system here, right? But I didn't say where these 2 qubits are. And the measurements are independent, right? So in principle, I could measure this one computational basis in 1 qubit, another computational basis in the other qubit, and these are the outcomes I would observe. So in principle, 1/2 of the system could be here, and the other half of the system could be at the other end of the universe. Okay? And what we're saying here is that I could measure my system here, and I know that when the being at the other end of the universe measures their system, if I observed 0, I can be sure with probability 100% that the other being will also measure 0. But we didn't have to communicate. We didn't have to the outcome will be random, but it will be perfectly correlated, right? And this is something strange and interesting. And we could have a whole lecture series about this, but we don't have the time. So I just wanted to maybe quickly brush over this fact that when you have composite systems, things become a bit more complicated, and you have these weird phenomena like states like this one, where you have perfect correlations even for independent measurements. And this is not something you can have classically in some sense that can be made precise, but unfortunately we don't have the time. Okay, so I guess there's still 4 minutes, but it's not worth continuing with a new subject now. So maybe I take the last 4 minutes for questions and feedback. Like, I don't know if I was too slow, if I was too fast, if my handwriting was terrible, anything I should change so that we continue tomorrow in a better way. Any comments? Too fast, too slow?
What I think is that maybe the audience will watch the recording is maybe mathematicians, and the audience here maybe is more physics. The background, maybe? Yeah. Which is something that we were not expecting.
Okay.
So I think the lecture would establish a common grounds for the invention of theory. I think it will be mostly useful for the people watching the recording.
Okay.
So maybe that was also related. But I think very much looking forward to the next session.
Okay, cool.
If there's some comments.
But general pacing, was it too fast or too slow? I guess Ruben's comment was that was too slow, or do the others agree? Should I move faster tomorrow?